Hello everyone, welcome to this online material characterization course organized by NPTEL. In the last class, we have just looked at some of the statistical methods to analyze the micrographs where we want to calculate the volume fraction of the second phase or the the size of the second phase, how to do that and what are the statistical methods available and so on. So, I would like to continue that tutorial class. We will just recollect what we have seen in the last class, and then I will also talk about the kind of errors, standard propagation errors or standard errors, whatever we have just seen in the last class. And then I will just take you to the actual problem solving using some of the standard micrographs taken from optical microscope or the scanning electron microscope and so on. So, if you recall what all we have seen in the last class as a statistical methods for metallographic analysis, you will recall that we have looked at volume fraction VV and then length fraction LL and point fraction PP and so on. So, let me continue to So, if I recall, I have introduced a term as standard error multiplying constant T 95 n minus 1, where 95 is the, we are looking at the data, that is a random data for 95% of confidence level, and then we would like to look at the significance of this. Though I introduced this, I did not talk about in length. So, let us look at the significance of this, and this constant is depending on number of measurements on a random sampling. So, how this constant is getting influenced by number of samples as well as the degrees of freedom, that we will see. So, if you look at the graph which we have already seen in the last class also, the standard error multiplying constant varies with the number of measurements small n like this, and then you can see that after it reaches beyond 20, the T95 n minus 1 error constant stabilizes around 2 beyond 20. Okay. So, you can that I have just mentioned this in the last class. So, we can recall this, we can write this. So, if n is greater than or equal to 20, the T95 n minus 1 try to stabilize around 2. This is because you can write it in the bracket, because T distribution approximates to a normal distribution. So, when n is equal to 20 or greater than, n is equal to greater than or equal to 20, the constant remains 2, because the T distribution approximates to a normal distribution. So, now what I will do is, we can even mention the degrees of freedom here, this column. So, let us start from 0. This is 10, 20, 30, 40, etc. This is n minus 1, that is degrees of freedom, that compares with the number of experiments. So, what I will do now is, I will just give you some values in a form of table for 95% confident limits as a function of degrees of freedom or mu, which is nothing but n minus 1. So, that you can have the ready reference for this, how this constant varies with the number of experiments. So, let us plot mu versus t so if it is 1, So, you have the value of mu, that is degrees of freedom, with t up to 10. So, I will give you a few more for the reference, mu and t, maybe 15. I will give you, for example, 2.131 and 20, 2.086, 30, 2.02. So, you may find these values in some of the standard textbooks also, but this is just for the ready reference for you to calculate the degrees of freedom for the t, and then you can use these values for the statistical methods which we are going to use for calculating various microstructural parameters or stereological parameters. And now, what I will do is I will briefly discuss the propagation of errors, and before that let us recall the 95% probability that so this is the formula which we have seen in the last class, just to recollect, because we have now tabulated the t for different degrees of freedom, where you have the 95% of probability that the population mean value lies between this range. So, all the stereological parameters whatever you measure should be represented or should be presented in this form if you really want to take care of the accuracy or the most meaningful values of your statistical analysis, then this is considered useful. So, let us now look at the propagation of errors, because it is very important that one should know what is the error bar you have for your data, and also you should know how the propagation of the error goes along with the number of measurements or the kind of samples you do, random sampling and so on. So, what I have written here is, when a variable z is a function of two or more independent variables, say x and y, which must be measured experimentally, like your one of the stereological parameters like volume fraction or something like that, that is z is equal to function of x and y, the standard error or the 95% confidence interval of z depends on the weighted average of the standard errors of x and y as s z bar whole square is equal to s x bar whole square times dou z by dou x whole square plus s y bar whole square times dou z by dou y whole square, plus like that it will propagate depending upon the number of variables. If you have z, then the z term will again x y z term also will come. We can write the same thing in the other form. So, when you have the variables x and y, the standard error propagation is written like this. For example, you can have variables of this form, then the standard error is written in this fashion, or you can also write this equation divided by the relative standard error, then you have the s z bar divided by z bar whole square in terms of s x bar by x bar whole square times n square plus s y bar by y bar whole square times m square. So, for example, if you are interested in measuring the grain size or a colony size and etc., we should use the error estimation and then present the results. So, these are the brief introduction of all the statistical methods what I have been talking about. Now, what I will do is I will just take out some practical example how these statistical methods are actually evaluated. from the micrograph which is taken through optical microscopy or scanning electron microscopy. So, in that first exercise what I will do is I have few slides to show you. If you look at this slide, this is the micrograph taken from a steel sample. You are seeing the bright white background and a dark patches. This is a microstructure. Those who are not familiar with this steel microstructure etc., you can also consider this as a two-phase microstructure, where you have the white as a matrix and the dark patches are second phase. And for those who are familiar with the metallurgy of steel, this is a ferrite pearlite microstructure. So, what I want you to concentrate on this, how to use a graticule in a microscope, optical microscope, to find out a volume fraction using a point counting method. So, that is the idea. So, you have to just use some of the graticule in the eyepiece of the microscope. So, that is why it is shown in a circle. Suppose you take this micrograph at the magnification of 100x, then if you use a graticule So, what I have written here, the results which I am going to present on the blackboard is obtained when a 4-point graticule which I showed on the slide was moved on 100 different positions on the using the microscope. So, our interest is to find out the volume fraction here. So, but here we are trying to find out the point fraction in each area, that is P, P, I in this example is P P I is equal to P, here it is written that black phase is called perlite phase, it could be anything in your case. So, just for a clarity I have written it is a P divided by 4. So, we can write before I write the other formula. So, what you have to understand here is using this probe 4-point graticule, you can get 3.5 or 4 or even 0. So, those probabilities are there. Let us see what kind of values we get for measuring these values. So, the same thing can be written for the average values for n number of counting. So, you get So, what I have done is here is a big table, but it is still worth to go through it one by one, so that you will be able to appreciate what we are going to see in the volume fraction counting method results. So, you have the column 1 has the number of points in perlite or the black phase, what I have shown in the micrograph. This is the number of areas counted, so which is 100, because I said here 100 different positions the graticule is moved. So, sigma Ni is equal to 100, and the point fraction in perlite ppi, and n times ppi, and then it is n times square of ppi. So, now I will also write how do we get these each of this. So, the first one, the point fraction is taken from this, and the average PP is taken from this. So, you have this sigma Ni is 100, sigma Ni PPI is also available in the table. So, you can write just for the reference, column 2 gives the raw data, column 3 is obtained using this formula. For example, you say 1 using 1, column 4 and 5 are the products of from column 2 and column 3. So, you have some, so this is a raw data according to this micrograph. Column 3 is obtained using this equation 1, and column 4 and 5 are the products from column 2 and 3. So, 2 and 3 you get this, and then of course, this the simply a square of this. So, what you will see here is, so you can just let us write here, the value is about 17.50, and here this is 6.15625, and if we can substitute the same thing here, so this is what you get as the average PP, that is a point fraction. If you use the 4-point graticule moved on a different position on the micrograph what I have shown. So, this is the final value, but now we have to calculate the standard error. How to do that? So, simply we know that the previous class I have shown how to calculate the standard deviation. So, you can directly take that formula and substitute these values. So, we can calculate the standard error from this. Standard error is P P S of capital S, which is nothing but 0.177. We have used this formula in the, so which is nothing but, you can write it so on the 95% confidence limit is 0.0354, and thus your P P bar is equal to 0.175 plus or minus 0.035, or you may round it off to 0.8 plus or minus 0. 0.04. So, the point fraction lies between these limits, and that is how the data is represented finally with the 95% of confidence limit for this simple point counting method. So, what is important here is you have to remember that the number of sampling is important. The more the measurements, the more the accurate will be, and then you generate all this statistical data carefully, and then calculate the standard deviation and then standard error, and present the final data with the 95% of confidence limit like this. So, we can look at the similar analysis in the calculating the volume fraction using a linear analysis also, like mean intercept length also we can do that. I will just demonstrate that in the next class. Thank you.